What up, Chem Gang? It's Jeremy from the Chemistry, and today we're going to be talking about atomic radius. What is it, and what influences it? The atomic radius is a great tell for the size of an atom because of the way that it's defined. It's defined simply as the distance between the center of the nucleus and the outermost valent electron shell. Let's draw a real world parallel with this thing. Let's say you were a dressmaker or you made pants and every member of your family came to you to be fitted for a pants or for a dress. Would the size be the same? No. And likewise, the same way how every person in your family, in your community, in the world has a different size, so do atoms of different elements. And while the size of persons are determined by a plethora of factors, such as your diet, where you're actually from, your genetics, your activity, and just whatever else, atomic radius, on the other hand, is influenced by two simple factors. The first is the strength of the nucleus, which is tied in directly to the number of protons that you have, and then secondly, the number of inner shielding electrons. Firstly, the protons are positively charged and the electrons are negatively charged, and in the world of science, opposites attract. Therefore, the more protons you have, the more pull you will have for these outer valent electrons, and the effect that will have will be that will decrease your atomic radius because you will be forcing your atom to condense, basically. Number two, your number of shielding electrons. Now, your electrons are negatively charged, and you also have a type of electrons that are not inside of the valence shell. The electrons that are not inside of the valence shell are all on the inside, and they're called inner shielding electrons. They have this effect of basically soaking up a good majority of the pull of the nucleus, so that less of the pull, no matter how many protons you have, less of the pull from the nucleus is felt by the actual electrons in the valence shell. Now, let's look at changes in atomic radius as we traverse the periodic table of elements. Now, unlike the sizes of persons even in your own family, which will vary completely random, the changes in atomic radii along the periodic table of elements are actually very predictable. Let's look at what happens to the atomic radius as you go down the group. As you can see in my picture, lithium, we're looking at group 1 here, lithium, which is at the top of group 1, it's very small, while sodium, which is right below it, is bigger in size or has a larger atomic radius. Now let's explore why. Firstly, sodium has more electrons than lithium and therefore also has more electron shells. Lithium only has 2 electron shells while sodium has 3. And so, because you've added an entire electron shell, you automatically increase the radius. Go figure. But not only that. What happens in the case of lithium and sodium is that you actually increase the number of shielding electrons as well. So not only do you add a completely new electron shell, but you increase the number of shielding electrons. In the case of lithium, there are only 2 shielding electrons. Well, in the case of sodium, you have 10 shielding electrons. Remember what we said inner shielding electrons do. They shield the valence shell electrons from the pull of the nucleus. They reduce the field that those valence shell electrons feel. Let's look a little deeper. It is actually possible to calculate the pull that the valence shell electrons will feel from the nucleus. And the way that we do this is to take the number of protons and subtract the number of inner shielding electrons. Just go figure. If you have 3 protons, like in the case of lithium, but those 3 protons all have a charge of +1, the pull that the valent electrons could feel is +3. However, if you also have 2 inner shielding electrons reducing that pull, then you have to account for that. So you take 3 protons and minus 2 electrons, and in the case of lithium, the valence shell electrons feel a total net charge or pull from the nucleus of +1. Now in the case of sodium, guess what? You have 11 protons and you have 10 electrons, and therefore the overall net pull that those valent electrons feel from the nucleus in sodium is +1. Did you notice something? That's right. In lithium and in sodium, and guess what? All other group 1 metals, they all feel a charge or a pull. The valence shell electrons all feel a pull of +1 from the nucleus. No, that +1 has to go through more inner shielding electrons as you go down the group. And it's the same +1 for all the atoms of group 1 elements. So therefore, the more shielding electrons that you actually put in, the less pull that these valent electrons are going to feel, and therefore they can be a little bit further from the nucleus as you go down the group.